Hello students, welcome to the 10th lecture on the topic sequence and series. So in this we were talking about the power series. So let's start with an example, like we were already doing examples, and so we will just, for brushing up, we will do an example and then we will do different topics like term by term integration and differentiation under this power series. So let's start with an example. So this is my series which I called it as An. Now you know how to start checking the power series is convergent or divergent for which value of x. So we will apply the ratio test for the mod of this series so that we can find out for what values of x the power series converges absolutely. Okay, so we see that we are getting this. Now this is our limit, it is free of n, so limit will be this. Now this limit converges if the value of this limit is less than 1. You know the ratio test, and when the series converges when this value of limit will be less than 1. So I will write for convergence the value of limit should be less than 1. Okay, so from this what we will get, this implies that I will get this. Now this implies that mod of x is less than under root 2. Now by this expression what do you find? We find that our radius of convergence is root 2 and the center is also root 2. So we can write, if I call it as equation 2, equation 1 is already taken here, I call it as equation 2. Now from equation we have the value of x. You can easily see that I can write it as this. And okay, so what did you find? That for this values of x the power series converges absolutely. And so the summary, you can write the summary till now. The center, that is your A, is under root 2. The radius of convergence is also root 2, and interval of absolute convergence is 0. This, and interval of convergence, if you talk about interval of convergence, you know that if it is absolute convergent, it is also convergent. So this is the interval of convergence also. So you know that from 0 to 2 root 2 your series will converge absolutely. You know when it is greater than 2 under root 2 and it is less than 0, the series diverges by the nth term test. Now you don't know what will happen at two values, that is for x is equal to 0 and x is equal to 2 root 2. So the next task or the next step will be to find the nature of the power series at these two endpoints. For other values of x, you already know the nature of the series. So let us find out what will happen at the end point. So at end point x is equal to 0 and 2 root 2, we will check this. So I will start with at x is equal to 0. This is my A part. So the series 1 at x is equal to 0, series 1 will become, see, you have to put x is equal to 0 in this, so you can easily see that you will have a series like this. I'll name it as Bn, that is at x is equal to 0, series 1 is Bn. So this is equal to, now you can easily see that I can write this as So if you take the power, what you will get? You will get 2 to the power n. So this and this got cancel out. So you are left with the series, that is your series Bn will be equal to summation of this. Okay, now what you can do is that apply the nth root test. Suppose that I take mod of Bn so that I can check that what will happen to the series absolutely. So my mod of Bn will be equal to this. Now you can easily see that limit of n tending to infinity Bn is equal to root 2, which is not equal to 0, and therefore summation of mod Bn is divergent. And you also know that if the nth term does not go to 0, the original term also diverges by nth term test, and therefore you can also write that since limit of n tending to infinity Bn is also not equal to 0, therefore summation of Bn is not convergent by nth term test for divergence. So what you can say that this series, the power series, does not converges even conditionally at the point x is equal to 0. Now let us see what will happen at x is equal to 2 root 2. So just I will write it out that therefore summation of an is divergent and is neither absolute convergent nor conditional convergent. Okay, at x is equal to 0. So I hope this is clear. So now we will go to this point when x is equal to 2 root 2. Now when we put the series 1 becomes, you can see if you put 2 root 2 in this series 2 root 2, what you will get? I will write it as Cn, and this will again become to the series. Okay, now you already know that this is a divergent series, which is already shown because the nth term does not go to 0, and therefore it is divergent. You have already shown. So what did you find? That at x is equal to 2 root 2, summation of an is divergent, and it is neither conditional nor absolute convergent. So what is the summary? So I will write out the final summary. You already have find out the center was equal to root 2, the radius of convergence was equal to root 2, and the interval of absolute convergence will be the same. And interval of convergence is also equal to the absolute convergence, because we have seen that at these end point our power series diverges. It neither converges conditionally also. So we will not add this equality over the end point. Okay, now we will talk about the term by term differentiation theorem. So let us write the new heading. Now what does this term by term differentiation theorem means? Like this theorem gives that if we have a power series, then we can differentiate it term by term for each of its interior points in the interval of convergence. Like we have this interval of convergence, and you can differentiate the power series in each of the interior point within this interval of convergence, and whatever is the resultant power series will also converge for the same interval. So let us write a power series can be differentiated term by term at each interior point of its interval of convergence, and the second is the resultant power series obtained, like after differentiating term by term, the power series obtained is also convergent at each interior point on the interval of convergence of the original series. So this was the basic idea. What do you mean by term differentiation? So let us write the proper statement for this theorem, term by term differentiation theorem. Now suppose if you have a series, a power series, because it has a power of variable of x, so this is a power series. This converges, suppose that this converges for this interval where r is greater than 0, then it defines a function f of x such that, like, you can write a function which is equal to this, and it is also defined for the interval of the convergence, like it is an interval of convergence, so this function is defined for all the x in the interval of convergence, and such a function has derivative of all order inside interval of convergence. Okay, so we can obtain the derivatives by differentiating the original series term by term. So what can we do? Like, we can find f dash x. So you can find out f dash x, this will be equal to, okay, so you differentiated this and you will get this, and then if you double differentiate you will get, and so on. You can differentiate up to any order. Now each series which is derived, this and so on, each series which is derived is also convergent for every interior point in the interval of convergence of the original series. Like, this was the interval of convergence for the original series. So what we can say about this derived series, that they are also convergent for each of the interior point in this interval of convergence. So I'll write it down that each of these derived series converges at every interior points of interval of convergence of the original series. Okay. So now let us consider an example. So if I take example for this, consider a power series. So you have this power series which you know that you can expand and write it like this, which is your f of x. Let us call this equation number 1. Now you know that this is a type of geometric series and it converges for mod of x less than 1. That is that x, if x is in between -1 to 1, we will say that this power series 1 is convergent. Now differentiating term by term, we get, obviously we are differentiating it on the right hand side, term by term, so I'll get, so this will be our f dash x, and which will be equal to, you can easily see that you can write this as n x to the power n minus 1. Now I'll call it as equation number 2. Now you can see that now the resultant series 2 is also convergent for x in between -1 to 1. That is what was the interval of the convergence for the original series. The interval of the convergence for the derived series is the same. Okay, so now we will see another theorem, that is the term by term integration theorem. Okay, so this is same as term by term differentiation theorem. It says that we can integrate the power series term by term at each of the interior point of its interval of convergence, and the resulting power series that is obtained is also convergent at all the interior points within the interval of convergence. So we will write it down. A power series can be integrated term by term at each interior point of its interval of convergence. And secondly, the resulting power series obtained is also convergent at each interior point of interval of convergence of the original series, what you have seen in the term by term differentiation theorem. So we will give a proper statement like we gave in term by term differentiation theorem. So I'll write, suppose that you have a series, this is your original series. Now this converges for this interval. This series converges for this interval for r greater than 0. Then the series this also converges for the same interval as the original series. This is, and what do you have, an integration of fx dx will be equal to this, and it will also converge for all x, for x that is in between a minus r to a plus r. Okay, so this is the statement for the term by term integration. That is, you have a original series that is convergent for this interval, then you can integrate it term by term, and the derived series will be also convergent for the x for the same interval. Like whatever you obtain will converge for the same values of x which they converge for the original series. Now there are 2 points which are like important notes you can take from these 2 theorems. First is, note 1 is that the term by term differentiation theorem may or may not work for other series such like the series containing such as series containing trigonometric series. such as series containing trigonometric function, or you can write like, so for example, if I say like I have a series which looks like this, now you can easily show that this is a convergent series for all x. Now when you differentiate it term by term, but when you differentiate term by term, you get a series. We get, now this series diverges, the obtained series, this series diverges for all x. So you have seen that this theorem, term by term differentiation, holds for only the series which is of this form. Any other series which contains like trigonometric function, the result will not hold true. This is an example that this was, the original series was convergent for all x, but when you differentiated it term by term, you get this, and it starts diverging for all values of x. Now secondly, the second note is the both theorems, you can write the both theorem only guarantees convergence of the resultant series inside interval of convergence, but not at end point. This means that you can say that if my original series is convergent for like a minus r to a plus r, then the derived series will also converge for all the values in between these. But it doesn't say anything about the end point, that whether the derived series will converge at the end point or not. So the resultant series may or may not converge at the end points, and it has nothing with the original series. It just guarantees that the resultant or the derived series will converge for in between the interval, all the points in between, but what will happen at the end point, we don't know, that it may or may not converge. Okay, so now we will start a new topic, that is the Taylor series and the Maclaurin series. So let me write down the heading, and then I will tell you what does this, like how does this Taylor series and Maclaurin series looks like, and what do we mean by this series. Now there are many functions which are infinitely differentiable, and that functions generates a power series that are termed as Taylor series. So let me first write down, and then I'll give you some examples so that you can get a clear picture that what does this Taylor series gives about the infinitely differentiable function. So I'll write the functions that are infinitely differentiable can generate a power series which is called the Taylor series. Now what is these Taylor series? It provides an approximation, the polynomial approximation for the functions which are infinitely differentiable. Like if we have a cos function, cos x, and we want to have a approximation of the cos x through the polynomial function, so this approximation is called as a Taylor series. So let us write down the definition, the proper definition of the Taylor series and Maclaurin series. Let fx be a function that has derivatives of all orders throughout some interval containing a as an interior point. Like you have a function fx and it has a derivatives of all order in some interval containing this a as a interior point. Then the Taylor series generated by fx at the point a is, this is k is going from 0 to infinity, so your Taylor series will be this. So till fn a n factorial x minus a and so on. So this is a Taylor series of function fx around the point this x is equal to a, and the Maclaurin series generated by fx is given by this. So you can clearly see that if you find the Taylor series around x is equal to 0, the series obtained is called as a Maclaurin series. Clearly I'll write that Maclaurin series of fx is simply Taylor series of fx at a is equal to 0. Obviously if you put a is equal to 0, you will get the Maclaurin series. So I'll do one example and give you the explanation that what does the series do with the functions. So now if you have a question that find the Taylor series of f of x is equal to 1 by x at a is equal to 2. Now we are asked to do what? That you have a function 1 by x and we want to see the approximation of this function around the point 2. So firstly use this series so that we can approximate the function with the Taylor series. So for using this, we need to find out f derivative of x, and then we will put a is equal to 2. Then f double derivative, triple derivative and so on. So let's start. So what we will do, we have to find the Taylor series of fx at point a is equal to 2 is given by fx will be equal to f of a is 2 over here. I am writing the journal first and then I will put a is equal to 2. This I call it as equation number 1. Okay. So now what I need to find is that f dash a, f double dash a and so on, and f of a. So since f of x is equal to 1 by x and a is equal to 2, so our 1 reduces 2 if I write, then 1 reduces to f of 2, f dash 2, you can write like this, and then f triple dash 2 x minus 2, this is also 2, 3 factorial and so on. Now this call it as equation number 2. Now what will be the value of f of 2? Since you know f of x is this, So f of 2 will be equal to 1 by 2. What will be the value of f dash x? It will be equal to minus by x square. So what will be the value of f dash 2? This will be minus 1 by 2 square. You can write 1 by minus 1 by 4. Now what will be the value of f double derivative x? This will be equal to 2 by x cube. And what will be the value of f double dash a? That will be equal to 2 by 2 cube. So this will be plus 1 by 4. Okay. So these are together, and then we will find out f triple derivative. This will be equal to this, and if you find out at the point at 2, this will be equal to minus 3 by 8. Now put this in equation number 2. Put all the values in this equation. That f of 2 is half, this f dash 2 is minus 1 by, and see what you get. So this will be equal to, putting values in equation 2. So this will be equal to, so if you see, your tailored series will finally look like this, and you can write it as, okay, so now you can clearly see that this is 2 square, 2 cube, 2 to the power 4, and so on. So I can write this this as equal to this. Now this is a geometric series. Okay, now geometric series have R as, you can easily see that this is a geometric series, and you have R as this value. Now this series converges for what value? You know that if mod of R is less than 1, then the geometric series will converge. So you can write, so the given series converges absolutely when mod of R is less than 1. This implies that mod of x minus 2 is less than 2, and this implies that whenever x is between 0 to 4, the power series converges. And also you can find the sum of the series is equal to, you already know that the geometric series has this sum, and if I put all the values, what I'll get 1 by x. Now you can see that the sum converges to this 1 by x. Like if I put, you know already that if I want to find the value of the function at x is equal to 2, so you will put at x is equal to 2, and this also shows that whatever is your approximation is also converging to this formula. Now in this sense we have a geometric series, so we are lucky to find that where the sum is converging, but there are many Taylor series which we don't know where does it converge, and we will look it later, the convergence theorem for the Taylor series. But till now you must have some picture that I took this fx 1 by x and I wrote it in the form of infinite series, and whatever will be the value of x at a is equal to 2, my infinite series is also converging to that point only. So one thing you can see that if you draw the graph, suppose that you have this function fx and you draw the graph, and what you did approximation. Suppose that I took only this much term, Suppose that I want to see what is the graph of the polynomial of these two terms. So if I plot, I'll get something like this, like around 2, that is A2, it will match, but further away from 2 it will have a little bit of difference. And if I take this, like if I consider now this also, like we considered 3 terms and then we plot the graph, what we will find that this will look like this. So you can see that from this graph what you have an idea that around A is equal to 2. This is our original graph. The original graph and the approximated graph are nearby equal, and if you consider more and more terms, you will see that all, like I have considered only 2 terms, I got this black one. When I considered 3 terms, I got this red one, and around A is equal to 2, you can see that this graph is like good approximation around this A is equal to or X is equal to 2. You have all the 3 graphs looks like a same in this neighborhood. But as we move away from this 2, we are getting a little bit of deflection. Here it is deflection, here it is deflection. So around X is equal to 2, you can see that the actual function and the approximate function behaves in the same way. So this is the beauty of Taylor series, that you can take the functions, you can take trigonometric functions like which are differentiable, and then you can approximate it with the help of a polynomial function. Now polynomial functions are easy to handle, easy to differentiate, easy to integrate, so it is easier to see the nature of something which is of the polynomial form rather than some other trigonometric function. So what can we do? We can approximate the function with the help of the infinite series. And if we say that around this A, that means that the approximation will be very good around this value, but it may differ. Like if we go far from this value, our graph may deviate, but around this the function will approximate a very good value. So I hope that you understand why this Taylor series is very helpful. Like for another example, if I draw this is my, suppose that this is my graph of cos x. Okay, now you can easily find that if I expand or if I find the Maclaurin series of cos x around this 0, I'll get 1 minus theta square or x square, sorry, x square by 2 factorial plus x to the power 4 by 4 factorial and so on. And if I take only these 2 terms and plot, I'll get a graph like this. So you can see that around x is equal to 0, the approximate curve is nearby to the curve of cos of x. And as you increase, like you just consider and you saw this, and if you consider this, you will get more close to this curve, and then you start getting, so you will get more better approximation of this cos x function near to the x is equal to 0. So Taylor series is mainly the study of taking the non-polynomial functions and finding the polynomial approximation. So I'll write it down. Taylor series study is about taking non-polynomial function and finding polynomial approximation near some input. So we will discuss Taylor polynomial in our next class. So I'll leave this lecture here. Thank you.